Okay, so good afternoon, everyone. So this is a pleasure to restart the ReNewQuantum seminars. Our speaker this afternoon will be Johannes Branahl. We'll talk about non-commutative, what happens when non-commutative QFT meets blobbed topological recursion. So let's listen to his talk.
Yeah, good afternoon, everyone. So first of all, I would like to thank all the organizers of this ReNewQuantum seminar, especially Bertrand and Na, who invited me to speak here during the conference and summer school in southern Italy in September. And yeah, it's a pleasure to speak here. I will be speaking about today about non-commutative quantum field theory meets blob topological recursion, and how blob topological recursion gives us some new path towards exact solution of QFTs. And we think currently, due to the discovery of TR-like structures in our quantum field theory, being the Grosse-Wolkenhaar model, a long-term project seems to come gradually to an end. And today I would like to retrace some important steps that led us to the path towards topological recursion in our quantum field theory. And of course, I have to mention that the current work wouldn't have been possible without my collaborators from Oxford, which is Alexander Hock, from Münster, which is Reimer Wolkenhaar, and Harald Grosse from Vienna. And to get an overview what all this is about, let me briefly present some history of this project. So, wait a second, what happened? Ah, now it works. Okay, sorry for that. So let me briefly retrace on the path of the Grosse-Wolkenhaar model towards topological recursion. So in the 90s and the early 21st century, non-commutative geometry based on the groundbreaking works of Alain Connes and related researchers became also a very fruitful and promising area for QFT toy models. And this motivated Harald Grosse and Reimer Wolkenhaar in the early 2000s to construct a QFT toy model on a non-commutative space with a hope to find an exact solution. And I mean, a natural starting point in quantum field theory is often the two-point function, the easiest natural object, a correlation function also called the propagator. And in 2009, Grosse and Wolkenhaar found a nonlinear integral equation determining the two-point function alone, which is really exceptional in quantum field theory, because often you have to know the four-point function, for instance, for the two-point function, the six-point function for the four-point function, and so on. So there's an infinite stack breaking down in this model, which already yield the group some hope that solvability might exist in this model. However, it took almost 10 years again to find a solution of this nonlinear integral equation. First, they found in a sleepless night in Les Houches together with Eric Panzer a very important special case of this equation, and found that the two-point function is solved in terms of the Lambert W function. And based on this special case, it was possible to make like an educated guess how the solution of all quartic matrix models look like. I will later specify what all quartic matrix models mean, but based on this general solution, it was more or less easy to read out the ingredients of the spectral curve, later being responsible for the topological recursion behind the model. And indeed, we found in 2020 some TR-like structures. At the beginning, we weren't sure about how it exactly works, and then we found out, read about the existence of blob topological recursion. And based on a very interesting symmetry in the spectral curve, that y of z is minus x of minus z. Yeah, based on this very simple relation and the solution of these all-quartic matrix models, it was possible even to formulate a proof, at least in the planar sector, genus 0, in two different ways, that our quantum field theory is governed by block topological recursion. And the big questions for the future are, of course, the structure of the non-planar sectors, including also the free energies in block topological recursion. So we already made some progress for G equals 1, but there's a lot of work to do, and the great goal at the horizon is, of course, integrability. Is there really the hope for an integrable quantum field theory? And I would like to show you some hints that this might be a reasonable hope or assumption. So let us go back to the beginning. I mean, in quantum field theory, there was a big success of unifying the fundamental forces of nature. Think about the electro-weak interaction. But still, general relativity, meaning gravity, is decoupled from quantum field theory. Maybe someday it won't be anymore, but then a suitable space will be needed, and this will be a non-commutative one. And let me now present our non-commutative space we are dealing with. So the idea behind is a non-commutative product of quantum spaces that extends our usual understanding of products of quantum fields. And this is called the Moyal product. So let us have a look at this star product of G and H, both being Schwarz functions, so with rapidly decaying derivatives. And what is going on there? We have in the argument of G a shift by this object theta, which is defined below. Okay, we have some easy matrices here. We have a skew-symmetric matrix and a very important scalar parameter, V, depending on the dimension D, which somehow describes how non-commutative your space is. So consider, for instance, that V is going to 0. What is happening there in the integrand? Okay, we have this exponential e to the iky. We simply obtain a Dirac delta distribution, and after integrating out, we end up with a usual product, right? However, we are in our non-commutative quantum field theory interested in the opposite limit. So we send V to infinity and see what happens. And the natural link to topological recursion emerges due to the existence of a matrix base of the Moyal algebra behind. So you can express everything by a basis of Hermitian matrices, together with this normalization condition when you integrate the matrix space out. And this gives the possibility that you can expand your quantum field phi from the Schwarz space into that matrix basis. And maybe one remark, talking about quantum field theory, you usually have to incorporate time, but this is very complicated here, speaking about Wick rotation and all this stuff. So we are focusing today on a Euclidean quantum field theory. Time is another chapter, which is really challenging. However, let us have a look how we can get from our non-commutative quantum field theory to a matrix model, so to say. So, as usual, in a good quantum field theory, let us start from starting from an action functional S of the quantum fields phi. Okay, what do we have here? We integrate out our quantum fields over a d-dimensional space and have a kinetic term here, which is sandwiched by a Moyal product of two quantum fields. And this kinetic term contains a Laplacian, which will be later responsible for the external field in our matrix model. Then for the experts, we need to introduce in the beginning of the theory an oscillator term, like a harmonic oscillator, in order to avoid a mixing of ultraviolet and infrared divergencies. But this is very QFT stuff. We will forget about all these QFT details today. Of course, the particles can also have mass, mu squared. And the interaction happens in this last expression here, determined by the coupling strength lambda. And here we have a fourfold product, making this action functional in the end, a non-commutative real quantum field theory with a quartic interaction of these scalar quantum fields, right? And if you remember now, there is a matrix space. You can integrate out these quantum fields in that base, and what remains is simply a trace of phi to the 4. And we can even simplify this action functional if we go to the so-called self-duality points, setting this oscillator term to 1, omega to 1. Then also the kinetic term becomes a matrix product. So in the end, we are dealing with such an object here with an external field E made of the Laplacian. And now we can incorporate our action functional into an exponential, forming a partition function where we integrate over all Hermitian matrices. And the exponential contains like the size of the matrix, number of eigenvalues, and the external field, and here our quartic interaction. And I'm sure you have already seen the partition function of the Kontsevich model. It is very similar. We simply substituted, so to say, the cubic potential by a quartic one. And that is why we call, nowadays in our papers, the model we are investigating also the quartic Kontsevich model, being a special case of the Gauss-Wultenham model with all these simplifications, self-duality point, and so on. Okay, we already encountered a few times this dimension D, and let us now briefly have a look where this dimension is coming from. So we can use for it a very old theorem from the physicist Hermann Weyl in the beginning of the 20th century, where you can attach a spectral measure to the spectrum of our Laplace operator E, and you can read off more or less a canonical dimension belonging to the spectral measure if you simply take the infimum of a real positive number m, so that the integral using this spectral measure and this denominator is still convergent. Then you have like a real number, take the Gaussian bracket, and now you have the dimension of our quantum field theory. Going back to this Q-symmetric matrix, you might have already seen that only even dimensions are allowed. And I've listed some examples we are investigating on the D-dimensional Moyal space. And this is on the one hand, like a trivial quantum field theory, where D is simply 0. Here we have a discrete spectral measure and a truncated energy spectrum of the particles, whatever this might be. There we have a multiplicity of the eigenvalues of the external field, which is arbitrary. The multiplicity becomes 1 if we take a spectral measure, trivial, like we set d rho t equal to dt, and simply integrate over it. We have a continuous spectrum in 2 dimensions, and the same happens in 4 dimensions as well if you use a linear measure, like another additional factor t dt. In this case, the eigenvalues would have a different multiplicity, namely n. So possible eigenvalues would be 1, 2, 2, 3, 3, 3, and so on. So there our dimension comes from, Weyl's theorem. And now we should keep our eyes on the objects which are interesting in this quantum field theory. And of course, yeah, as usual, they are correlation functions like 2-point functions, 4-point functions, and so on. And they carry some topology. So first of all, they have a genus expansion. And if you have a look at the indices, they form, yeah, a disjoint union of a union of disjoint cycles. So let us have a look what happens on the right hand side. We interpret our correlation functions as cumulants of our quantum fields, with which are generated by simply deriving our partition function with respect to these matrix indices. And here you see these building blocks, right? So starting with P11, both are matrix indices, and we form a cycle here and ending exactly here. And then we continue and form, in general, like B cycles of a certain length. So in principle, this set of indices can be also expressed as a union of B disjoint cycles, having every time the length ni, for instance. And if you have read maybe the work of Elba Garcia-Failde on fully simple maps, you might remember, okay, it is exactly the same definition. And indeed, there is a correspondence if we perform a Feynman graph expansion of our correlation function into fat Feynman graphs. We only generate like fully simple quadrangulations. I will comment later on that when we go deeper into perturbation theory. The only difference are the weights or the decorations due to the external matrix E. And in the beginning, I already mentioned the starting point of the exact solution of our quantum field theory. It is necessary to understand the solution of the nonlinear integral equation. Okay, here we have sums due to a discrete measure with some Dirac distributions, but in principle, it is a nonlinear integral equation. So what is happening here? We complexify our correlation functions G in a proper way. We will see later how it works, and have now our 2-point function as a complex valued function in 2 arguments. And the goal is, so to say, find all quartic matrix models, or find the solution of all quartic matrix models if you are able to solve this nonlinear integral equation for any spectral measure, for an arbitrary measure. And this includes, of course, also the finite case, the quartic-Kontsevich model, but also many interesting cases more, as we will see now. So the solution itself of all quartic matrix models is again encoded in an integral equation, in a linear integral equation. So it is all contained in a variable transform, one should say. We call it R of Z, dependent on the dimension D. And what is happening here? Okay, we can solve this equation by inserting a deformed measure, deformed spectral measure with respect to the coupling constant lambda. And what might that be? Okay, you take a non-deformed measure, rho 0, which is made of these delta distributions, and then you insert our variable transform R of Z into the non-deformed measure to obtain a deformation, and then you can in principle write down R of D. And there are, of course, some cases where you can write down a solution. So let us first focus on the finite case. In this case, we can write down our 2-point function in terms of this variable transform R of Z. Let us have a look what is happening there. Why is it a variable transform? Okay, remember the eigenvalues of our external field E. And you can now perform like a pullback using this function R. to go into, let's say, in the Z plane here, where we have deformed eigenvalues epsilon, and to each eigenvalue ek, you can calculate in principle an deformed eigenvalue epsilon k. And now our definition or solution of the two-point functions contains, on the one hand, these variable transforms R of Z. We re-encounter also the multiplicities of the eigenvalues and these epsilons, also including all other pre-images of the epsilons. So think about R as a branched covering of the Riemann sphere, and it has a d+1-fold ramification. So you can also find d other pre-images of the epsilons, and we denote them by epsilon hat. And now you see, okay, you have a very complicated expression even for the two-point function. And now the goal should be for an exact solution of this quantum field theory to write everything down based on the two-point function. But maybe you already see, okay, this will not lead that far, because terms will be extremely awful, I would say. So we have to keep our eyes on objects in our quantum field theory that simplifies things a lot. And here topological recursion enters the stage. The important step is to interpret this variable transform R of Z, also maybe in d dimensions, as the constituent x of that of our spectral curve, later determining our topological recursion. So in 0 dimensions with our truncated energy spectrum, this is of course a bit trivial for quantum field theory, but it is still not easily solvable, but in principle solvable in the context of topological recursion.
Ну, меня это не удивляет.
What do we have for a spectral curve here? Okay, in 0 dimensions, our function x is made of this sum, or also containing a derivative x. So you see, it is something quite complicated. It can be only solved implicitly. So in this case, we just call it x of z and do not really care about all the internal structure, because it cannot be written down explicitly. We just keep in mind that there are 2D ramification points of this curve. And as I've already shown you, inserting these epsilons into this ingredient of the spectral curve, you get back the eigenvalues of the external field. And now you have 2 ways we investigated so far to send this d, the size of the matrix, to infinity. And there's one choice in 2 dimensions where you end up with a fairly easy curve, I would say. You just obtain this logarithm, and we assume at least that there can be a relation to Hurwitz's theory. This log is very characteristic in other spectral curves in topological recursion, but here really everything becomes fairly hard to prove, because our Dyson-Schwinger equations of the quantum field theory aren't finite sums anymore. They are integral equations where no concrete solution theory is worked out yet. So here we have to motivate some things, maybe perturbatively, but this is a very complicated realm. Still a nice curve, and in 4 dimensions with a linear measure, everything becomes very difficult, although it is of course the interesting case for physicists, because dimension 4 is obviously corresponding to our world, but also in other toy models, everything becomes horrible in 4 dimensions. That is the reason why we have not much progress in 4 dimensions yet. You can see here that our the solution of this integral equation I've shown you before for this variable transform R of Z becomes a Gaussian hypergeometric function, which is of course a terrible spectral curve later for topological recursion, and it is it contains a parameter alpha depending on the coupling constant lambda. And it can be written down as an arcsine. This object is rather interesting in another context. I just want to mention it very quickly. So you can again formulate, according to Weil's theorem, a spectral dimension belonging to 4 dimensions, and the spectral dimension has like a dimensional drop. We have 4 minus 2 times this arcsine, and this is at least interesting for quantum field theorists, not in topological recursion, but it guarantees the non-triviality of the quantum field theory. Otherwise, yeah, all the effort would be a bit in vain if we are dealing with a trivial QFT. So this is still a very important result, but we will focus on the finite case in 0 dimensions. Okay, topological recursion. When I prepared my slides, I wasn't sure if it is completely known to everyone. So yeah, if I bore you, might get a coffee for the next 3 minutes for this slide. So what is topological recursion? It is topological in the sense that we are looking at objects having a genus G, a number of holes, and a number of Torelli marked points, forming together an omega Gn plus 1. And it is recursive in the sense that we can construct this omega Gn plus 1 in 2 different ways. Okay, the recursion starts with the unstable topologies, meaning positive Euler characteristic, omega 0,1 and omega 0,2, and both these objects define you a recursion kernel, which is denoted by K. And now you can construct the left-hand side recursively by gluing the recursion kernel in 2 different ways. There's, on the one hand, the way that you simply take an object with 1 hole less and glue it at 2 different points, forming another hole, the missing hole, and you have back your omega Gn plus 1. The other option is to glue 2 different objects here and sum over all possible partitions. You can decompose your variables and your genus. So you say G1 plus G2 has to be the genus on the left-hand side, and the same is has to be guaranteed for these subsets I1 and I2. And what is happening mathematically? It is simply a residue formula. When you glue something, you take a residue because your objects omega Gn have poles at the ramification points, and these are the important points, ramification points of your x of z, where you pick the residues. So what is happening here? You can either set Q and the local Galois involution into the same object and you create 1 hole more, or you can distribute Q and sigma of Q to different objects. So what is sigma of Q exactly? The local Galois involution, not necessarily global. You have to pick 1 pre-image of your x of that, so that nearby a ramification point, you have an equality of x of z and x of the Galois involution of z. And both functions meet at the ramification point itself. So inserting beta I, the ramification point, into sigma, we have beta I again. It's a fixed point, and for sure it cannot be the trivial involution. It cannot be the identity, it has to be something else. So Kontsevich model, for instance, x of z is z squared. So the Galois involution is fairly simple. It is simply minus z with a fixed point 0 for both Galois involution and z itself. Okay, so how can we implement our quantum field theory into this framework of topological recursion? So a quantum field theorist would first assume that our correlation functions G are the important and natural objects that might be governed by topological recursion. But that is not the point. So when we investigated a special case in the beginning of 2020, we realized, or it was all based on an idea of Alexander Hock, that you have to keep your eyes on, we call it a generalized correlation function, meaning that we create some indices more here by simply deriving with respect to different eigenvalues of the external field. So on the one hand, you will need these generalized correlation functions. And on the other hand, you have to interpret these derivatives as a boundary creation operator, which gives you later the objects governed by topological recursion, or blobbed topological recursion later on. So you might introduce a formal free energy, and deriving with respect to these energy eigenvalues, you obtain your omega GM, okay, up to some, you might know this renormalization procedure for omega 02. But to be precise, in the end, there is simply a very easy transformation of these big omega GNs after complexification to n complex variables. If you just subtract, which is also common, the potential V or its derivatives, then you have to multiply all the differentials dx of z I in the n variables, and also to be precise, we have to multiply it with our coupling constant, but this is not that important, I would say. So we will need both objects to solve our omega GNs in a triangular pattern. So how does it work? How can we generate our omega GN to make a conjecture how the structure might look like? We start with omega 01 and identify it with the two-point function itself, which was, of course, the starting point of all our solution procedure. And then we can go on. Based on the two-point function, we can create, on the one hand, this 1 plus 1 point function, where we have inserted another boundary, and the omega 02 as well, from which you can go on to a generalized two-point function, which is the requirement to solve the equation for omega 03 and so on. So you can get into the realm of the pair of pens on the one hand, and on the other hand, you can go one genus higher, the torus topology. You need this 1 plus 1 point function to solve your equation for omega 1. Then you go on with a genus 1 2-point function and so on. So in principle, the solution theory can be written down, and you have solutions of all generalized Schwinger-Dyson equations, only using this interesting triangular pattern. So what do these omega GNs look like? Let us start with the unstable topologies forming our recursion kernel. So the disk amplitude is looks like the common disk. There's nothing to say. It is simply y dx, of course, dependent on the complex variable z1. However, we have this ravishing symmetry here of x and y, which I've already announced y of z is equal to minus x of minus z. So it is sufficient in the coming steps, identifying this x with this variable transform r of z, and together with this symmetry, everything will be constructed from this mysterious function r of z. And the global symmetry will affect all higher topologies. You already see it when you have a look at the cylinder amplitude. You have your usual Bergman kernel, standard bidifferential. Okay, we have genus 0 spectral curve. Therefore, it is only this one with a pole, double pole on the diagonal. But for some reason, this symmetry also generates a reflected Bergman kernel, where you just flip a sign of one variable, so you have a double pole at the anti-diagonal. And I should leave a warning here that only the standard bidifferential will be taken into the recursion kernel. So nothing will work if we take also this reflected Bergman kernel into the recursion kernel, starting the recursion. And yeah, later on it has indeed to be interpreted as a blob. So it gives you already some hints that we are dealing with a generalized topological recursion. Before we go on, let me briefly comment on these omega 0, 2 with two marked points. I've shown you that the correlation functions cannot be the right objects. Okay, even the 2-point function was an awful object, which is really terrible to calculate with. But we see here, even for genus 0, where at least the first 2 lines survive. Okay, we have on the left-hand side something extremely easy, right? Only Bergman kernel plus reflected Bergman kernel. And on the right-hand side, we have all this garbage here, but as a sum, everything, yeah, comes together to this very simple expression. And this might be also a lesson for theoretical physicists, which are always focusing on the correlation functions themselves, doing Feynman graph expansion, dealing with very complicated objects. But maybe one is indeed looking for the wrong objects in QFT, right? We cannot say it so far because it is only a QFT toy model. But at least here we have seen that a clever rearrangement of all these correlation functions to different objects, the omega GNs, simplifies everything enormously. And you can also proceed and write down a very lengthy formula for omega 0,3 and so on. And this simplification, yeah, we interpret as yeah, at least one reason for this deep algebraic structure behind our quantum field theory and the appearance of exact solvability, because this happens not so often in QFT, of course. So let me now go on with the stable topologies, which are really created from the recursive framework. For instance, the pair of pans topology, which was found in 2020. After having performed this solution procedure of the Dyson-Schwinger equations, we end up with an object like that. And the interesting question might now be, okay, based on our spectral curve, we already know, can we construct our omega 0,3 using only topological recursion? And the answer is no, because you see, okay, this looks very, yeah, similar to TR. It is indeed the TR part, which can be generated using simply the TR formula and our spectral curve, only containing the standard bidifferential, as I already mentioned. But here we are, yeah, here we are struggling with a weird rest term, which is, although you can see it here, which is holomorphic at the ramification points, and it cannot be created by usual TR. And the interesting question is, of course, now can we unraveling a possible generic structures behind all these holomorphic remainders? So they are, of course, necessary. In the end, we have to create something symmetric. And because we do not take into account the whole omega 02, we are dealing here with a non-symmetric expression, and we need this rescuing terms to obtain something symmetric again. And something similar happens also for higher genera. When we solved the Dyson-Schwinger equations for omega 1,1, we don't only have this phenomenon with this sign flip of the variable. No, we also reach here the fixed point of this global symmetry between x and y being simply a 0. And yeah, now the big question is how to put this into some general formula. And luckily there is indeed a framework developed by Gaëtan Bourreau and Sergei Shadrin in 2015. So consider a model which does not really fit into the TR picture. Okay, you see it shares some similarities, it shares some characteristics, but there is a holomorphic add-on, like in our example. Then you can rescue the complete recursive formula if you allow for like an infinite stack of initial data, like this colored object here below. So you still have the same topological recursion, plus always this holomorphic add-on. So this infinite stack of initial data is successively contributing to the omega GNs on the left-hand side at each recursion step. And yeah, as we have already seen, we can decompose these three objects now in the two TR objects, having poles at the ramification points, and into this holomorphic add-ons, having some poles elsewhere. So, for instance, the 0 we have seen for genus 1, or also simply at the anti-diagonal. Again, see the great importance of the sign flip in our spectral curve. And indeed, this is the key to the general solution of our omega GNs. There is a generic structure behind. So after we had solved the first simple topologies up to omega 05 in the Dyson-Schwinger equations, each of us three formulated a conjecture how it might go on. And the interesting fact was that all three different conjectures were equivalent, and the equivalence was needed in the proof, in a combinatorial proof, or at least demanding lots of combinatorial effort by Raimar Wultenhaar, who had a free semester in the winter term. And yeah, based on all this effort, it was possible to write down a solution. And also Alexander Hock found a very interesting way of proving it, which was fairly easy once one already knows the structure. And now I invite you to take a look at this formula. So we have the usual in the planar sector, the usual TR formula, determining the polar part. And then for the holomorphic part, later forming the blobs, we have something astonishingly similar. So we have the same arrangement of subsets here. We have a holomorphic recursion kernel, which looks astonishingly similar or almost equal. The only difference is that in the TR part, we are dealing with residues at beta I, so with a fixed point here at the Galois involution. And for the holomorphic kernel, we take into account the residues at the anti-diagonal of all spectator variables. So consider this object here with the important variable z and this subset of m spectator variables, what you have to do is not only picking the residues at the beta I, but also at each anti-diagonal here, at each minus UK, you sum over them. Okay, for technical reasons, we have to introduce here an external derivative with respect to this UK, and here we have to calculate the primitive, but it can be easily done. And then we have a closed formula in block topological recursion, which is exceptional so far. So there are some models governed by BTR, and here really, we really have an explicit formula how to create all the blobs in a very interesting way. So very similar to topological recursion itself. And maybe this underpins also a current conjecture that you can always transform, or at least in some cases, transform block topological recursion to topological recursion using a different spectral curve, maybe going one genus up. This is, of course, very speculative at the moment, but at least we have some closed formula. And now we try to go on for higher genera. And within the proof, it became also clear that the linear and quadratic loop equations are fulfilled. So we can be, it really gives us a reliable proof that our quantum field theory is governed by block topological recursion. And so far, we have only concentrated on the Quarticon-Savage model itself. Maybe I briefly show you where to find this model in the realm of other matrix models. So starting from the famous Con-Savage model, having a global Galois involution, which is simply minus z, we can make it a bit more complicated and substitute the cubic potential. And what is happening here? Okay, the global symmetry now becomes what used to be the global Galois involution. The Galois involution in the Quarticon-Savage model is instead locally defined only and very ugly. You cannot really write it down just in terms of some Bell polynomials and so on. It is not that important to know it explicitly. And both models have the special case if we shrink our external field down to a scalar, then we cannot really distinguish our partition function from that of the Hermitian one matrix model if it is simply counting only triangulations or only quadrangulations. And here something similar happens. We have another type of a simple Galois involution, and let us make it everything a bit more complicated, going to two matrices, or maybe also a complex matrix, M and M dagger. And what happens is exactly the same. Now the global symmetry can be written down, at least in some special cases of equal potentials, that y of z is equal to x of 1 over z. Maybe it's an accident. We don't know so far, but comparing these two types of generalizations or making something more complicated, you see the similarity. We have to interpret all that someday. Maybe one last remark: if we turn off all the blobs, we can also enter the realm of the Hermitian 2 matrix model, but all this is under current investigation. So I would spend the last few minutes on perturbation theory in two completely different limits that might be interested for you, either if you are interested more in maps, or on the other hand, if you are more interested in QFT related stuff and also number theory. So a perturbative expansion works, as it is pretty well known. So you have correlation function like the 4-point function, where we have 4 of these ribbons here. In usual QFT, you have simply lines, but due to the matrix character of our model, we have these fat Feynman graphs or ribbon graphs, and we expand our correlation functions in powers of our coupling constant, which is the weight of the vertex here. So going to lambda squared, you can introduce some loops here, causing another weight lambda. So in the end, we have lambda squared, some graphs here, where you introduce the loops, the internal loops. And now we can keep our eyes on either the combinatorial limit, where you set D, so the matrix size, to 1. We have a scalar external field and are back in the realm of enumerative geometry. In this case, it is a simple power series with some coefficients, and these coefficients are very important. I already announced that the G's form fully simple maps. And indeed, if you expand everything in a power series, the numbers only count the number of Feynman graphs at each order in perturbation theory. And by duality, the ribbon graph and the ribbon graphs also have their dual, the fully simple map. And in the QFT limit, it goes into a completely different direction because, the physics picture of this loop is, a particle is propagating, then it might decay into a virtual particle-antiparticle state, which can have, of course, every momentum, every energy, and then it goes back into the simple propagator. And to take all these possible energies into account, you have to integrate out the whole spectrum. So every loop, makes it necessary to integrate over. And in a continuous spectrum, you might send your cutoff, your energy cutoff to infinity as well. So the integrals often possess some divergencies. Therefore, you have to do all this renormalization stuff, renormalizing the quantum field and the mass, as it is usual in QFT. Who's an expert in that already knows. You can use these maybe a bit old-fashioned even recipes like Zimmermann's forest formula adapted to ribbon graphs to get rid of all these divergencies. So, the first case, the limit of this external scalar enumerative geometry, I will show you maybe an interesting application. So you might remember the starting point of the recursion for omega 0, 1, where we just had the 2-point function contained. If we write it down for any genus, our quantum field theory tells us it has to look like this expression. And in this limit, we have again the Hermitian matrix model, as already announced. And to distinguish the maps from the right-hand side, we call and there's no doubt that for one boundary there's an equivalence to the Quartic-Savage model, because writing down the free energies being closed maps, there is no way to incorporate any requirement on the boundaries, because it has no boundaries, non-rooted maps. And also the loop insertion operator in our model and the Hermitian 1 matrix model, they are equivalent, at least going from the free energy to one boundary, like omega G1. And as an interesting application, let us set G equal 1, talking about ordinary tori. These ordinary tori generated by the Hermitian 1 matrix model can be sorted into two categories. On the one hand, the boundary can be simple, where the edges are not identified. And on the other hand, the vertices can be identified. So in this case, we would have a non-trivial cycle, I would say. And now let's turn to the right-hand side. Remember this definition of G made of disjoint cycles with the perfect bijection to the fully simple quadrangulations. These fully simple maps are now a subset of these ordinary maps, where only boundaries are allowed where no more than two belonging edges are incident to a vertex. And this work of Elba and Gaiton showed that it is simply governed by the Hermitian matrix model after exchange of x and y in the spectral curve. And remember the two categories of ordinary tori. These are exactly the two categories and these two functions on the right-hand side. On the one hand, the fully simple tori, but remember the non-trivial cycle. This will become a fully simple cylinder with a boundary length 1, 1. So a union of two disjoint cycles with boundary length 1 each. And the interesting thing about that is that for G equal 1, this relation was already known and proved in the studies of these fully simple quadrangulations. And interestingly, this starting condition for one boundary generalizes this result in enumerative geometry to any genus. And doing reverse engineering, knowing the nature of the graph expansion of the omegas and the G's, we would be also able to write down this the starting condition only using facts from enumerative geometry. So an interesting interplay. And now we finally enter a completely different realm, namely, as I've already told you, in this continuous spectrum, okay, we have, let's say, n loops in our Feynman integral, and now we have to integrate them out, loop by loop. And we can write down a generic loop integration recipe, and it looks like the right-hand side of this equation. And what is the left-hand side? It is a hyperlogarithm with some additional parameters. The interesting fact about integrating out these Feynman graphs in the QFT limit is that evaluated at the concrete boundaries, like the highest energy, the energy cutoff, which is 10 to infinity, evaluated at these boundaries, the hyperlogarithms also create multiple zeta values. So we have an interesting object from number theory in our quantum field theory. And now think about possible algebraic invariance of maybe block topological recursion in the QFT limit. What might that be if you now expand this invariant in a power series in lambda? It would be simply become a generating function of like multiple zeta values of objects from number theory. So this is of course all a question for the future, but maybe it brings some new input into topological recursion. The only serious hindrance, I've already mentioned it twice or thrice, that the Schwinger-Dyson equations become really awful in the continuous limit because of these complicated integral equations and so on. So the only way to make some progress is, at first, at least, to do some perturbation theory and expand possible invariance and compare the right-hand side, so the correlation functions, with possible invariance of block topological recursion. But like I said, all this is work for the future. So there are still many riddles waiting for us. On the one hand, demystifying the structure for the non-planar sectors, also taking the free energies into account in BTR, and on the other hand, the QFT limit, which hopefully creates some dialogue again also with the pure quantum field theorists, and that hopefully also brings some number theory into topological recursion. But we will see what the future will bring to us. So I, for my part, I'm done. I would really thank you for your attention. I hope I didn't run out of time, so there might be some time left for questions. So thank you very much.
Thank you, Johannes. Yes, you're right on time. Thank you very much for your talk. Is there any questions? So we should look at the chat. Or people ask questions directly.
May I ask a question?
Yeah, go for it.
Hi, Johannes.
I can do.
So I have one naive question. So in your definition of partition function, you don't have any capital D in it, right?
Capital D?
Yeah, I think you choose capital D to be 0, 2, and 4, and you get different spectral curve.
Yeah, exactly.
And
so,
do you have that capital D in your definition of the partition function? I probably just missed it.
I mean, the partition function is
of the matrix model.
Left untouched. I mean, we have like the zero-dimensional case where n is still a finite matrix, but I mean, you can also go into this continuum limit, so you don't really have to incorporate the dimension of the quantum field theory explicitly into the partition function, because all the information is contained in the external field, and by Weil's theorem, you will obtain the dimension out of the spectrum of the external field, right?
So is that correct to think that, so you have this definition of matrix model, and you take some limit, and depends on the limit you get these different values E, or
yeah, exactly. So the eigenvalue spectrum of E will determine your dimension of QFT.
Okay, yeah, thank you. Yeah, so that was a nice question. And the second question is actually, this is the question I asked you in Italy, but you might have figured out. So are there any topological gravity interpretation of this model?
So to be honest, I haven't spoken yet with the other group members about that. So the question was about Kontsevich model and its relation to quantum gravity.
Yeah, right. So the Kontsevich model has 2D gravity.
I mean, the idea is to triangulate the space. I'm really not sure if it would work for quadrangulations of your space, which would be the analogy here. I'm not an expert on this, to be honest. Maybe if some group member is listening to me, he might interrupt and enlighten me as well.
Okay, yeah. Thanks.
Is there any other question? Okay, in fact, I will ask a question myself, Johannes.
Yeah, please.
Well, several questions. In fact, yes, following the question by Kanto, in fact, so it is known that you can relate topological recursion to some integral over modulary spaces, and you use that somehow with the Hurwitz numbers at some point. But this can be done more generally, and indeed that's where there will be a link with something like topological gravity, or I would say generally something like I don't know, a kind of string theory. I mean, some integrals over moduli spaces. Did you look at that?
So far not. I mean, this Hurwitz conjecture is simply a bold conjecture. We haven't tried it out yet because of this symmetry. You would also have the log in your y of z, and as far as I remember, all this Hurwitz numbers and generalizations always have polynomials in
no, they can, no, typically they can have logs.
Okay, so yeah, it is something very new to us, all this intersection theory and moduli spaces. We have never been into this realm so far, so there we really have to learn a lot. But this is also, of course, a future goal to understand the intersection theory concretely, also for these higher dimensional spectral curves, indeed. But yeah, we haven't done progress so far.
Okay. Another question, you mentioned a link towards integrability, integrable systems. And you see, we find this kind of structure with poles at reflected points, typically in algebras like BKP. I mean, in case like BKP, or I mean, in overlay algebras, and the A sequence.
Yeah.
And I don't know, maybe this is a hint that your integrable systems has to do something with a BKP or something like that. But basically, what have you already found about integrable structure of your model?
No, we haven't found it yet. So currently we are investigating an interesting hint which goes in the same direction. We got it during our conference in Münster, also going into this BKP hierarchy direction. But yeah, also that is work in progress. So we also have the hope maybe to transform the the BTR back to TR. In this case, I guess we would already know that there has to be integrability. But I mean, it would be also interesting to know if integrability appears in BTR as well.
Yeah. Is there any other question?
Yeah, Bertrand, could I ask a question?
Yeah.
So, you know, is there anything that sort of conceptually stops you from looking at other potentials? So you have 5⁴ here, but I mean, in principle, you could look at sort of power series in phi, right? And in particular, there are sort of cases of specific models where we know that if you take a specific potential, you actually get counts that gives you RNA diagrams. So this is something that I worked on together with Bob Penner and Christian Reides and Lonya. And so it could be quite interesting to see what is that sort of on the physics side if you take this matrix model that gives you the counts on RNA diagrams.
Yeah, that's true. I mean, a quartic interaction is maybe the most natural interaction. I mean, you wouldn't expect some quintic terms also in
but this would involve
more physical QFT. But at least I'm aware of this generalized Kontsevich model where the other authors were taking into account an arbitrary potential, giving rise to these R-spin intersection numbers. Yeah. But we cannot really transform their partition function into ours. So this goes indeed in another direction, but it could be very interesting indeed.
So this sort of very explicit formula for which potential you have to take so that it gives you the RNA diagram counts. And those we sort of solved in very special cases. And so there you might have the starting point of what you were reducing to and telling us about for this 5⁴ model.
Could you say it again? Which diagrams? How are they called?
They are RNA diagrams. So they correspond exactly to the diagrams that one finds in RNA.
Biology, if you want.
Sorry?
Biology.
Biology, yeah, RNA and biology.
Okay, interesting. Thank you so much.
Thank you.
Okay, Johannes. Well, in fact, I would probably have more questions to ask in private. I mean, we can release people who have been attending. I mean, unless there is, so we have. I think we have still time for a couple of more questions. Don't hesitate, please. Okay, I think that people well, have finished the questions. So thank you a lot for your seminar.
Yeah, thank you. It was a pleasure to speak.
It will be available.
Yeah.
On the video also, Yana is taking care of making the video available. Thank you for your presentation.
Yeah, thank you.
Thank you, everyone.